You write a text view in XML or call text in Compose, and text appears on screen. Simple, right? But think about what had to happen. Something had to figure out how big the text should be. Something had to figure out where to put it. And something had to figure out where to put it. And something had to figure out what color each pixel should be and send that to the display. This is the rendering pipeline, and it is one of the most elegant pieces of engineering in Android. 3 passes: measure, layout, draw, turning a tree of objects in memory into a grid of colored pixels on a physical display. Today we are going to walk through each pass, understand what triggers them, see what makes them slow, and learn why the way you structure your views has a direct impact on performance. If you have ever wondered why constraint layout is faster than nested linear layouts, this video will make it crystal clear. Before we talk about rendering, let us talk about what is being rendered. Your UI is a tree of view objects. At the top is the deco view, the root that the system creates. Inside it is your layout, a linear layout containing a few text views, or a constraint layout with a dozen children, or a recycler view whose children are dynamically created. Every visible element on screen is a view, or a view group in this tree. And when it is time to render a frame, the system traverses this tree 3 times, once for measure, once for layout, once for draw. The larger and deeper your tree, the more work each traversal requires. This is the fundamental reason flat hierarchies are faster, fewer nodes to visit, fewer operations per frame. The first pass is measure. The question being answered is, how big should each view be? This starts at the root. The root view is told by the system you have this much space available, the full screen minus the status bar and navigation bar. The root then asks each of its children, given this much space, how big do you want to be? Each child calculates its desired size based on its content, its layout parameters, and the constraints from its parent. A text view measures its text, accounts for padding, and reports back. An image view measures its image, considers the scale type, and reports back. A view group measures all its children first, then calculates its own size based on how its children arrange themselves. The key thing to understand is that measure works top-down. The parent tells the child the constraints, and the child reports back its desired size. This happens for every single view in the tree, every single frame that requires remeasurement. Once every view knows how big it wants to be, the second pass begins layout. The question now is, where does each view go? The root view is positioned at the top left of the screen. Then it positions each of its children within its own bounds. A vertical linear layout places its first child at the top, then the second child below it, then the third below that. A constraint layout uses its constraint equations to calculate exact positions for each child. Each view receives its final coordinates, left, top, right, bottom, defining its rectangle on screen. Like measure, layout is a tree traversal. The parent positions the children, and if a child is itself a view group, it positions its own children within its allocated rectangle. At the end of this pass, every view knows exactly where it sits on screen and exactly how big it is. Now comes the fun part, drawing. Each view is told to draw itself into a canvas. A canvas is an abstraction over a drawing surface. The view can draw text, shapes, images, colors, whatever it needs to express itself visually. A text view draws its text string. A background drawable draws a filled rectangle. An image view draws its bitmap. The draw traversal goes through the tree, and each view draws itself. Then its children draw themselves on top. Views that appear later in the tree are drawn on top of views that appear earlier. That is how the Z-ordering works. But here is the important detail. With hardware acceleration, which is on by default since API 14, views are not drawing directly to the screen. They are recording their drawing commands into a display list, a serialized set of instructions like draw a rectangle here and draw text there. That display list is then handed to the render thread, which sends it to the GPU for actual rendering. This is a big deal because it means the main thread does not have to wait for the GPU. What triggers these passes? Two methods you should know: invalidate and request layout. When you call invalidate on a view, you are saying my appearance has changed, I need to redraw. Maybe the text color changed or a background color was updated. Invalidate triggers only the draw pass. It does not trigger measure or layout because the view size and position have not changed. When you call the request layout, you are saying my size or position may have changed. I need to be remeasured and repositioned. Maybe the text got longer or padding was changed. Request layout triggers the full pipeline: measure, layout, and draw. This distinction matters for performance. Invalidate is relatively cheap because it skips two of the three passes. Request layout is expensive because it starts from the beginning. And request layout does not just affect the view you called it on, it propagates up the tree to the root, because if a child changes size, its parent might need to change size too, and the parent's parent all the way up. Now let us talk about one of the sneakiest performance problems: double taxation. Some layouts need to measure their children more than once to figure out the correct sizes. A classic example is a linear layout with layout with stitch. The first measure pass calculates how big children want to be naturally. Then the linear layout sees there is leftover space that needs to be distributed according to the weights, so it measures those children a second time with the adjusted sizes. Each child measured twice means the work doubles, but it gets worse. If you nest a weighted linear layout inside another weighted linear layout, the inner one's children get measured 4 times 2 for the outer, times 2 for the inner. Add another level and it is 8 times. This is exponential growth. 3 levels of weighted linear layouts means each leaf view is measured 8 times per frame. This is exactly why DP nested layouts with measurement-heavy parents cause jank. Constraint layout avoids this by solving all constraints in a single pass, which is why it exists. Let me go deeper on what happens after do pass. When your views record the drawing commands into display lists, those display lists are handed to the render thread. The render thread is a separate thread, not the main thread, that is responsible for talking to the GPU. It takes the display lists, optimizes them, and issues OpenYL or Vulkan commands to the GPU. The GPU then rasterizes everything, turning those vector drawing commands into actual pixels in a frame buffer. This architecture is great for performance because the main thread can start working on the next frame while the render thread is still rendering the current one. They work in parallel. If your draw commands are simple and your display lists are small, the render thread finishes quickly and the frame makes it to the display on time. If your views are complex with lots of custom drawing, gradients, shadows, and clipping, the render thread takes longer and you might miss the frame deadline. Overdraw is when the GPU draws the same pixel multiple times in a single frame. Imagine you have a white background on your activity, then a white background on a fragment, then a white background on a card, then text on the card. That pixel under the text was painted 4 times, 3 layers of white backgrounds, and then the text. Each time a pixel is painted, the GPU does work. Painting it 4 times means 4 times the GPU work for that pixel. Multiply that by 1,000,000 pixels and you have a real performance cost. Android has a developer option called Debug GPU Overdraw that color codes your screen. Blue means 1 overdraw, 2 draws total. Green means 2 overdraws. Pink means 3. Red means 4 or more. You want to minimize the red. The fix is usually to remove unnecessary backgrounds. If a parent is already painting a white background, the child does not need one too. Remove the redundant Android background attributes. In Compose, be careful with modifier. Background, only apply it where truly needed. If you are using Jetpack Compose, the pipeline looks different on the surface but follows the same principles. Instead of view objects, you have composable functions that emit a composition, a tree of layout nodes. Instead of measure and layout as separate passes, Compose does them together in a single traversal, which is actually more efficient. Compose also prevents double taxation by design. It uses intrinsic measurements that are resolved in a single pass. The draw phase works similarly. Each layout node records drawing commands, and the render thread and GPU still do the final rendering, but the biggest difference is recomposition. When state changes in Compose, the framework does not remeasure the entire tree. It only re-executes the composable functions that read the change state. Then only the affected parts of the layout tree are remeasured and redrawn. This is called smart recomposition, and it can be significantly more efficient than the view system, where invalidate and request layout can propagate widely through the tree. Let me bring it all together. Every frame, the system traverses your view tree for measure, layout, and draw. A flat tree with 20 children has 20 nodes to visit. A deeply nested tree with the same 20 views might have 50 total nodes because of all the intermediate view groups, the linear layouts inside frame layouts, inside relative view groups, the linear layouts inside frame layouts. More nodes means more work per traversal. But the real danger is measurement multiplication. Each level of nesting can multiply the number of measurements. 3 levels of nested containers that each measure twice means each leaf is measured 8 times. Flat hierarchies avoid this multiplication entirely. Constraint layout lets you express complex positioning relationships without nesting, solving everything in one measurement pass. In Compose, the layout system is inherently flatter because you do not need wrapper containers for simple arrangements. This is not premature optimization. It is understanding the rendering pipeline and working with it rather than against it. Let us recap the rendering pipeline. Your UI is a tree of views. Each frame, the tree is traversed 3 times. Measure determines size. Layout determines position. Draw records rendering commands. Invalidate triggers only draw. Request layout triggers the full pipeline. Double taxation means some layouts measure children multiple times, and nesting amplifies this exponentially. The render thread sends display lists to the GPU for final pixel rendering. Overdraw means painting the same pixel multiple times, wasting GPU cycles. Compose follows the same concepts with a more efficient single-pass layout and smart recomposition. Flat hierarchies minimize traversal work and avoid measurement multiplication. In the next video, we are going to look at what happens when something goes seriously wrong, when your main thread gets so backed up that the system intervenes. That is ANR, application not responding. See you there.